Hello, my name is James Sebald. I'm from Prism Computational Sciences, and I'm here to tell you about one of our applications, Helios. Helios is a 1D radiation hydrodynamics code designed to study the hydrodynamic evolution of radiating plasmas. To see what this application can do, we're going to take a look at an example of a short pulse laser hitting an aluminum piece of foil. When you first bring up Helios, you're asked to define the geometry of your simulation. For our simple foil case, we'll be using a planar geometry. Next, we need to define the spatial regions of our simulation. To do that, we go to the Spatial Grid tab here. We only have one region, which is the aluminum itself. So first, we click the New Region button to add this region. We'll name this region as aluminum. We'll give the aluminum a thickness of 100 microns. We'll give this region 200 zones. One thing to note is the number of zones will cause the simulation time to scale non-linearly, so you need to factor that in when deciding how long you want your simulation to run for. Our region needs to have a mean atomic weight, which we can define right here. Luckily, we provide a drop-down of common materials, and aluminum is defined right here. We also need to define the mass density of our region, which is defined right here, and luckily we can once again use the drop-down to choose solid aluminum. Finally, we'll use 0.025 eV for room temperature for our initial temperature. Next, we need to define the equation of state of this region. To do that, we go to the equation of state tab here. We have a couple of different ways to define the equation of state. We can use Sesame data, Propaceous data, or different ideal gas models. We'll be using Propaceous data, which is provided with all Prism computational software. We need to define the location of the Propaceous data here, and then we can choose aluminum from the drop-down material list. Next, we need to define the opacity of this region. To do that, we go to the Opacity tab. We'll once again be using Propaceous data, and we'll choose aluminum from the drop-down. Finally, for thermal conductivity, we'll be using the Spitzer model as a default. Next, we need to define the hydrodynamics of the simulation. To do that, we go to the Hydro tab here. We'll be using the default energy model, but we'll also be using some advanced initial conditions. In order to prevent the unphysical expansions in the absence of external energy sources, we'll be using a quiet start. To do this, we'll set the temperature threshold to 0.1 eV. This will prevent any zone movement until the zone reaches the designated threshold value. Next, for the Atomic Processes tab, we don't actually need to do anything. Because our case is using pre-computed opacities and isn't using any CR capabilities, the options in this tab don't really come into play. For radiation transport, we'll be using the diffusion transport model and 200 frequency groups. This will be the resolution of our radiation field, and we could use a lower number when less resolution is needed, since the runtime of our simulation will scale with the chosen number. Next, we'll set up the short pulse laser for our simulation. To do that, we'll go to the Laser Source tab here and choose to include a single laser and make sure it's incident on the outer boundary of our foil. Now, we want our laser to have a Gaussian profile. To do that, we make sure we choose the Gaussian profile here. We'll give our short pulse laser a peak power of 1000 terawatts per square centimeter and a peak time at 200 picoseconds with a width of 100 picoseconds, like so. Helios also has the option to include several different types of external energy sources. These sources include particle beams, external radiation sources, and external magnetic fields. Though for this simulation, we're not going to be using any of these, so we can just leave them all as default in our simulation controls. Next, we'll go to time controls to control how long our simulation runs for. For our case, we'll have our simulation run for 2 nanoseconds. Next, we'll go to the Output tab, where we can set the output frequency of our calculations. For us, we'll be using an output frequency of 10 picoseconds, like so. Now that all of our simulation parameters have been set, we can click this Run Simulation tab. Because Helios is a Lagrangian code, the zoning distribution is presented to make sure everything looks sufficiently smooth. If all of the binning looks acceptable, you can click the Start Simulation button, designate an output for your run, and then begin the Helios simulation. Here, while Helios is running, you can see a progress monitor displaying different plasma properties such as temperature, pressure, density, and velocity. You also have the freedom to choose which variable you're plotting these properties against, such as radius, mass integral, initial radius, and zone index. Finally, when Helios has finished running, you'll be prompted if you would like to open the HydroPlot application to visualize these Helios results. And that brings us to the end of our Helios demonstration. If you have any questions or would like to request a demo, feel free to come to our website and reach out to us with any of our listed contacts. Thanks for watching.